What's up, everyone? It's Calc time with Miss Wesley. I am so excited to be here as always. And today we get to talk about big things. We are talking about the fun, emphasis on fundamental theorem of calculus, part one. And I am here in your integration packet 2, page 13. So while you're locating that or something to write on or something to write with, I came prepared. I'm going to dazzle you with some math jokes from this book I got from my niece, Matilda, 101 Math Jokes. So the first joke is, how did the dairy farmer keep track of his herd? How did he count his cows? Of course, he did it with a calculator, right? All in the delivery there. Why did the student eat his division homework? Maybe because the teacher said it was a piece of cake. Okay. And then just because these are so good, why doesn't the 1 hang out with the 2? Because you know what they say, three's a crowd. And then last but not least, what sport do 9 and 1 like to play? 9 and 1, they like to play, of course, tennis. All right, feel free to use those jokes on your family and friends. I've got a lot more where that came from, so just you wait. I was wondering if you could look at the top of page 13 here and pause the video while you try the warm-up. I want you to evaluate the integral they ask you for in number 1, and it looks like we need a rate of change, a derivative, in number 2. So I'm going to do the same. I'm going to pause the video, solve these, and then check back in. Okay, time in. I just tried that warm-up, and maybe you can check my answers here too. These are 2 huge things that we've been doing in calculus, right? We've just embarked upon a whole unit where we're taking integrals, and I had to integrate to get that first answer. And it's an indefinite integral, right? I have that plus the constant c at the end because there could be a myriad of different functions that would have this as their derivative. Right? Another thing we've done before, because it looks like the second one is a derivative, and we've talked informally about checking your answer for number 1 by what I just said, by taking a derivative and making sure that you get this original expression. Well, what we're dancing around is a huge, huge idea that was kind of introduced. If you look at these pictures underneath, we've got pictures of, it's kind of a walk down memory lane. In the very beginning of calculus, once we had tackled limits, we started to use them to talk about rates of change and slopes of tangent lines with differentiation. So I see in this picture, I want the rate of change maybe exactly at this point, so I could approximate it by finding the slope of a secant line, connecting the point to another point that's pretty close by. And calculus lets me take a limit that gets me to the actual slope of the tangent line at that point, right? They call this the tangent line problem. Well, now in integration, we're talking more about area under a curve. So I see we've approximated so far using Riemann sums, something called a definite integral. We want to find this shaded area here from the curve down to the x-axis. So maybe our first solution to the problem was, well, rectangles or trapezoids have pretty easy geometric area formulas. Maybe I'm approximating the curved area with the area of this rectangle. Definite integration should take us to an even better way to do this, right? We won't have to be approximating. Let me just move myself out of the way. Can I do that? Okay, there I go. Now I'm in the middle. We can take a definite integral that'll give us exact area under this curve. Well, did you notice there's a couple dudes at the top of this page? We have here some statues that are in Oxford right now, and they are statues of the 2 fathers of calculus. So I don't know if you've ever heard of them, but they are Mr. Isaac Newton and then also Gottfried Leibniz. Sometimes I forget the pronunciation of that last name, but there's a whole calculus controversy about these guys. So I don't know if you've been hearing about this, but back in the early 1700s, the controversy was who really discovered calculus, who really was the father and made most of the contributions. And the followers of one might have said that one plagiarized the works of the other, but in common day, we all kind of agree. It seems like the 2 discovered most of what we know as calculus today independently from one another. And one big thing that they both discovered is called the FTC, the fundamental theorem of calculus, and it's a huge connection we're about to make. And this is part 1. We'll kind of do this in 2 parts. It says if f is a continuous function on the closed interval ab. So this is huge, right? We have to make sure first that our function has no gaps in it over the interval in question. Then what it says is the function g defined by g of x is a definite integral from a, right, the lower bound of that interval, up to x. So think about what we're talking about here. We're talking about some kind of function, and I guess it says the integral of f of t. We'll call it f of t. And you are continuous on the closed interval from a to b, like that. And it looks like all of that would be the area under the curve from a to b, but we just want to go to some x value that's on this interval. So we're going to say the definite integral from the constant a to x, let's put x here, right, is going to be equal to this function g of x. We're going to call g of x the definite integral. Well, g of x is also continuous and differentiable. So if you start with a continuous function, its antiderivative is going to be continuous and differentiable. And this is the big part right here. The derivative of this antiderivative, the derivative of g of x, equals lowercase f of x. It equals this function evaluated at that variable x. So that all might seem a little bit tricky, but we can put this into layman's terms. In other words, differentiation and definite integration have a huge connection. They are inverses of one another. So I don't know if you know that you were invited to a wedding today. Did you get your invitation? Did it get lost in the mail? Luckily, I have my flowers here because this is a wedding, and flowers, I guess, are at weddings. This is a wedding between the two branches of calculus, the two major areas of calculus. You've got differential calculus, taking derivatives, finding rates of change, and then now we have integral calculus. And these two operations are inverses of one another. So in shorter terms here, you could say if the derivative of g of x is f of x, then formally, now that we know the FTC, the antiderivative of f of x is going to be g of x. And you see that in symbols here. If g prime of x equals f of x, then the integral of this, right, would take you back to the original g of x. This is what I think we're going to use to try a couple problems. I'm going to recopy this maybe at the top of the next page. Actually, it's kind of convenient here. If you want to flip the page, I want to put this expression at the top so we can use this FTC in a second. So it says if you take the derivative, the rate of change of an antiderivative expression, right, of a definite integral from any constant a to the variable x, as long as it's very, very important that this condition's upheld, the f has to be continuous on this closed interval from a to b, well then the integral of f of t, the function f of t with respect to t, these two operations are inverses of one another, so it's as if the d dx cancels with the integral from a to x, and all you have left is f of t, but it's evaluated at the variable x. So we're going to call it lowercase f of x. So it's kind of funny. It's a way that what you'll see on maybe standardized tests or on the AP exam are seemingly tough integrals to take, but they're just in disguise. They're easy questions in disguise, and I'll show you how that works. Number one doesn't look too simple. Number one says, in all these, the directions are use the FTC part 1 to find the derivative of the function. So they gave us an original function that is sort of kind of this form, of the form that you see up here. It's an integral from a constant 0 to the variable x of a function. We could call this f of t with respect to t, and look what they're asking us to do. They want us to take the derivative of a definite integral. I'm feeling very strongly that those two operations will have a canceling effect. Now, one thing I want to make sure I say early on is we have to make sure, I can't stress it enough, we have to make sure this function is continuous on the closed interval that we're speaking of. And I don't think we're going to run into too much trouble with this one because the function, and we're calling it f of t here, should be, and I'll write this, is continuous for all real t. If I plugged any t value, positive, negative, 0, who knows what, into this expression, I believe there should be no gaps in this graph, no skips, there should be no problem with continuity. So I'm going to call this function continuous on the set of real numbers, on all real numbers. So that shouldn't give us much trouble. Okay, so now to the part where I said this problem was supposed to be easy, or rewriting it should be easy. We want to take g prime of x. We want to find the derivative of the given expression. So g prime of x should just equal, it's the derivative of an integral, right, of this form, should just equal this thing evaluated at x. So we're going to take f of t, which was 1 plus t squared, and literally we're just going to plug in an x for t. This final answer is going to be the square root of 1 plus x squared. It's as if you didn't do much mathematically whatsoever, but you did a lot. You took the derivative of an antiderivative, and we had this form. Okay, let's try a couple others. I want to try some with a slightly different setup, and our goal is going to be early on with number 2 to get this expression for h of x to look more like what I see up here in the fundamental theorem part 2. So we're supposed to find h prime of x, but it looks like the format needs to have the constant on the bottom, and the x, right, the variable that we're plugging in, needs to be the upper limit of integration. Well, we know our integral properties, right? We've got a way we could figure that out. I want the x to be up top, like we said, and I know I can switch the limits of integration as long as I make the entire definite integral negative, as long as I take the opposite sign. So this is equivalent to the negative integral from 2 to x. This is much better. We've got our constant, remember, it doesn't matter what constant, on the bottom. We have a nice continuous trig expression on the inside, so I'm just going to recopy cosine of t squared plus t, and that's an integral taken with respect to t. So now I guess it's time to find the derivative of this integral, right? The derivative of this antiderivative. So h prime of x should equal, let me keep the negative there. I'm going to just do what we did last time. I'm going to take the x, I'm going to plug it in everywhere I see t here, and it's a derivative of an integral, so there's nothing more to change. So we'll put negative parentheses cosine, I'll just plug in x squared there carefully, and then plus x. X gets plugged in again. I'm going to leave it like that. You can decide if you'd rather leave it with the negative brought into the parentheses, but that looks pretty good. Okay, so now we got to get to something a little more interesting. So last one had the limits of integration kind of switched. Number 3 looks pretty good because it's already got the constant on the bottom, so I can check off that requirement. And it doesn't look like this expression is going to be discontinuous at any real numbers, so I don't think there'll be a problem with continuity here either. What we can do is we are going to basically, let's start this one. We're going to chain rule this one. We still can apply the fundamental theorem part 1 to get g prime of x, which says, okay, you have an integral expression, you want to take the derivative of it, so it should just be equal to this expression evaluated at square root of x. But since this is more interesting than just an x, and square root of x itself has its own interesting derivative that's not just 1, we're going to chain on the derivative of the inside, just like we would do in the chain rule for integration. So maybe I should put that here, chain rule, as a reminder. And can you help me with step 1? So let's plug in square root of x everywhere we see s here. We're evaluating s, what should I say? We're evaluating, what should I say, g of s at the square root of x. So here goes nothing. Plug in the square root of x squared, and then on the bottom, the square root of x squared plus 1. Now we're not quite finished, right? We mentioned this chain rule thing. Because we've got the square root of x here, can you tag on the square root of x's derivative? So that's like saying x to the 1/2 power. And let's use the power rule for differentiation. 1/2 x to the negative 1/2. Here's your answer all in terms of x. We can tidy it up a little bit before we leave it as a final answer, but this is pretty much, it's got all the components necessary for this answer. We've got the square root of x squared, that's just x. On the bottom, x, I think, plus 1. And that's multiplied by 1 over 2 times the square root of x. And maybe I'll just make that one fraction and not take it any further. So I kind of like this, 2 root x, x plus 1 with an x up top. So that added step of tagging on an inside derivative, otherwise it works the same way as all the others. Let's look at 4. 4 looks pretty straightforward. If you want to pause the video and try 4 on your own, it's already set up with the constant on the bottom and the variable up top. I think this one's going to be a straight plug-in. So pause or stay with me. Let's try it. G prime of u. I've got a nice continuous function. You're going from 2 to the variable u, so it's got a constant on the bottom. Let's just plug u in everywhere we see x, right? So we'll go u plus u squared and leave that one. Tune back in for part 2 because there's a couple other cases I want to make sure we cover together, and then you've got some more practice coming up. Okay, talk to you soon.